Hi, I'm Mike Crowley, and today at Fluid Mechanics I'm going to show you how to do a simple surge or water hammer of a rising main using the Wanda software tool. Wanda is a hydraulic modelling and software tool which we use for modelling longer pipelines where surge or water hammer, as it's sometimes called, and friction are the predominant factors. In today's video I will demonstrate what happens when you get a pump trip. Pump trips are usually the worst case for surge in a water main. You have a pumping station pumping fluid from a low level tank up to a high level tank or reservoir, and what can happen is that you get a power failure to the pumps, electrical power failure, and the pumps suddenly shut down, and that usually induces the worst case surge. Often what you need to do is put in surge vessels to limit these surge events, and that becomes the design case. I'm going to show you in this video how you size a surge vessel for a pump trip event. I'll show you this shortly at Fluid Mechanics. Okay, so this is the Wanda interface. We have where we build the model in here, and this is the properties window. I've done another video entitled hydraulic modeling using Wanda. This gives a bit more background into how to use Wanda, and I would recommend you look at that video if you want to find more out about how Wanda is used. I sort of assume in this video that you've got some sort of understanding of Wanda. Not that you actually need to understand how to use Wanda to understand the topics covered in this video, but if you want to get into the nitty-gritty of how I create the model, then you're probably best to look at that video first. So in this video I'm going to set up the pumping station pumping up to a high level reservoir. So the first thing we need is, I'm going to set it up as a tank. So we're going to have a reservoir. We've got a low level tank, and we're going to put in the height of this tank. So I'm just going to say that this low level tank has got a height of, and we're just going to put that in at 5 meters. We're going to need some pumps to pump up. Now normally in a pumping station you wouldn't just have one pump, you'd have a couple, you know, it all depends on the duty that you require, but I'm going to sort of assume that this has got 2 working pumps. Actually, what I'm going to do is delete one of the pumps for now, and we'll add it back in a minute, because it's slightly easier if I set up the one pump and then copy it across. So that's what I'll do. So we have a pump. We're going to set it up as a table. So basically, we're going to set up the performance of the pump of a table. Okay, so that's the data I'm going to use for the pump. I'm going to be having a head on the top tank of around about 40 meters, and then with the pump friction, you'll find that actually when we've got this thing working, I think we'll probably be able to get the pump so it's running somewhere in the middle of its pump curve here. Now, one thing you'll notice I've done is I've taken the pump curve all the way down to 0 head. Now normally you don't operate pumps all the way down here, you'd be operating them up the top, and actually if you went to a pump manufacturer and asked them for the curve, they'd probably only give you the curve halfway along. Now what you'd need to do when you get the pump curve is it is best to actually project it down. You can just put the numbers in. Okay, so that's that pump curve set up. So that's safe. So we've got a table for that. We need to put in the speed of the pump, and the speed of the pump, well, we'll just say it's 14 sort of standard speed, maximum speed. Okay, and the initial speed will be 1,480 euros. So it's going to start off at that speed. Initially, I'm going to just run the steady state case. So we're just going to work out what the flow is at the steady state thing. So we have a pump, and I'm just going to copy that pump, copy, paste. So we've now got 2 pumps. Okay, we're going to need, so I'm just going to assume that these pumps are, I'm going to make the assumption that most of the pumps nowadays, what you tend to use is what these wet well pumps or submersible type pumps. So we're just going to have a submersible pump inside a tank, so that's connected up to the tank, and then basically you'll have a piece of pipe coming out of the sump, and at the top of the sump we'll have some check valves. So we need two bits of pipe. And we're going to need two check valves, and I'll just put an ideal check valve for now. You can actually within this program put in the characteristics, closing time and that sort of thing, but for the example we do, this is not going to make much difference, so I'll just use an ideal check valve. So connect those up. So we have a pipe which comes out of the sump. On top usually you'll have a check valve, and if I just go to these components, I'll click both of them and I can set both of them up, the parameters up at the same time. Liquid, we will put in a pipe size, I think we'll just have these as 250mm diameter pipes. Friction model will be Colbert white, Wolf roughness 1mm. Dynamic friction. Of course we need to put the length of the pipe in, and this is just a relatively short length of pipe, and I'm going to say 5 meters, kept taking it out of a sump basically. What you can do here is we can copy, I just select all three. Okay, I'm going to put in there check valve of 250, same as the .250. I'll copy that across, and loss coefficient of say 1. Initially it's going to be open, correct. So that's the actual pumping station. Pumps in a sump, pipeline coming out of the sump, check valves at the top. Then we join those two pipes together, and we'll then actually have the pipeline going away. So we need a pipeline. In fact, what I'm going to do is I'm going to have two pipelines going up to the tank at the top of the hill, as it were, and it's going to be an undulating pipeline. And the reason why I've put two pipelines is in between the two pipelines I'm going to put an air vent. There's going to be a high point between the two pipes, and we'll put an air vent there. So we have a tank at the top. Okay, so now it's just a question of connecting these up together. Run that to there. So now we need to set up some levels and for the pipes and pipe lengths. So let's just first of all start off with the tank up here. I'm going to put the level of the end tank at 40 meters, and the connection to it we need to set to 40 meters. At this end here we'd set that's at 5 meters, and we'll set these ones here to 5 meters. Okay, the pipe comes up to the top of the sump, and it's going to go up to a higher level, which is going to be at 7 meters. Okay, the intermediate level between the pipes where we're going to put the air valve, I'm going to have at 15 meters. So I need to put in the profile for the pipeline. So we're going to change that to profile, and let's put in the profile. Okay. So let's try running the model and see what happens. We're going to calculate the steady state. elevation is missing. So that's run the model okay. So we can just check what flow rates we're getting from the system. So that pump there, these are steady state cases, so it just gives you the answer straight down here. And we got a discharge of 328 meters cubed an hour and a head of 65 meters. If we sort of look up the table I put in earlier on for the pump curve, that's sort of floating around or out between lines 3 and 4 there. Okay. The total flow rate from the system, so if we look at that pipe there, this will give you the total discharge, which is 657 meters. And what we can do here is we can look at the whole pipeline. So we can click the two pipelines together, and we can actually look at the profile along the main of what's happening to the head. Okay, so we start off at the start of the pipeline at 70 meters, and it drops all the way down to 40. What you've got to remember is that's the level plus the head on the pump. We start off at 70 and it just linearly decreases. That's basically due to the friction in the pipe down to 0. This is showing you the profile of the pipe. So it's basically starting off at 7 meters. It's going up to that high point at 15. It's then going back down to 5 meters in the middle, and then it's gradually increasing again to 35. So that's the steady state case. Okay, so now what we need to do is run a transient case on this. So we're going to need to set up the transient model. So let's go and do that. First of all, we need to do is change the mode of operation. So it's when you first start it, it's set up in engineering mode. We're going to go to transient mode. Okay. So what we're going to need to do is provide some more data now for this transient case, and what I'm proposing to do is actually in terms of pumps. Okay, one of the things you'll see down here is the polar moment of the inertia of the pumps. Now, at one time, people used to talk about, for preventing surge and that, using flywheels on pumps. And actually, if you wanted to, you could put a flywheel added in there. You could put quite a high moment of inertia. And that would actually act the same as a surge vessel. Basically, if you lost your power, the inertia of the pump would slowly come out and keep the pump going. However, it's not really very practical, particularly with submersible type pumps. And so I can't say I've often seen it using big flywheels. So effectively, all you're left with is the inertia of the motor and the pump itself, the whirly bits of the pump. And actually, they tend to be quite low in terms of inertia. So I'll, put 1 or 2. You can ask the pump manufacturer, and they'll usually give you some number to put in there. Now, these short bits of pipe aren't really going to have much impact on the water hammer, and because they're quite short, and if you look at my previous video, I talked about that this uses the method of characteristics. The length of the pipe with the fixed step solver is going to be too short to take into account using the method of characteristics. So what we do is we set up this as a rigid column. So effectively it takes the inertia of the thing into account, but it doesn't do the method of characteristics in those very short bits of pipe. These lengths of pipe, okay, this is where the water hammer or surge is going to take. So we're going to actually model it that way. We need to put in the wave speed. Again, I've done another video on calculating wave speed. If you want to, in here, we can actually put in the pipe wall thickness, Young's modulus, and using that, you can actually, it will internally calculate the wave speed. I personally just prefer to put in what the wave speed is, so I'm going to specify it instead. And we'll put in 1,200 meters. 1,200 meters. Okay, and I'm going to copy that across. Okay. So both of those pipes got now 1,200 meters per second as the wave speed. Let me just set up the transient case first of all. I think we need to set this up maybe. It's quite a long main. Sorry, change time parameters. Okay, sorry. Okay, so we're going to have a simulation time of 200 seconds and a steps size of 0.1 second. Okay, so every 0.1 second is going to calculate a result. We've put in the initial speed and we've got the drive steady, so we're actually going to put in a trip, a pump trip. Okay, and what we're going to do is we're going to put in a time 1 second. 1 second. Okay, so what that means is that when the model runs, for the first second it will be running in steady state conditions. That will produce exactly the same results as I did previously when I run the steady state court case. Then the pump trips and we'll see what happens, and that's what we're interested in actually modelling. Okay, so we could have a try and go, see if that model runs. I've probably forgotten something, but let's just see what happens. All right. No, it's run, so that's great. We'll just look at the discharge from that pipe. That one there, sorry. Okay, so this is actually showing you the discharge out of the pipeline. So initially it's starting off at 6, whatever it was previously, 650 something or other. And then obviously after a few seconds, well, the pump trips, but then a few seconds later it starts to come off, and then you just get this oscillating flow down the pipeline. Now, the point I'm going to show you is this one here. So let's look at the pressure that's actually at this high point in the system. Now, you'll notice here that after the pump trips, the pressure is actually going down to -1 bar. This is bar gauge, okay? So -1 bar gauge is 0 bar absolute. Effectively, it's drawing a vacuum in there. Now, the way I've set this system up at the moment would not be acceptable as a normal system. You've got a high point there. It wouldn't work anyway because with a high point, if you made a system like this, you just get air in the pipe and you get an airlock at that point there. You need to get rid of the air. So and you can't really have this type of arrangement. I mean, I can model it, but it's not really sort of an acceptable way to design it. What we need to do is put an air vent in there. So first of all, it allows you to fill the pipe up and get rid of the air, and it's going to stop this cavitation that's occurring down there. So unfortunately, when we put the air vent in, it's going to cause other problems, and then that's what we're going to have to deal with in terms of this pump trip. So we need to put an air vent in there to start with, and this is the, let me just get the air vent, which is that one there. So click that component, put it in. I'll connect it up to the pipeline, and we need to put in some parameters for the air vent. So elevation, this is how high the air vent is over the pipe. I'll just put 0, which basically means it's the same level. Laplace, this is the ratio of heat capacities, 1.4. Cp over Cv, is it? Air temperature, we'll just say it's 20 degrees C. 0.7. This is about the contraction as the air comes in and out. Vena contraction, or some people call it. It's coefficient of discharge, or whatever you like to call it. We need to put an area in there. Now I'm just going to use a 70mm area, 70mm valve, and I happen to know that is I think it's 3850 e to the -6 meters. Right. 3850 e to the -6. The initial volume is how much air is in the pipe already at the start, and we're going to say it's 0. And I'll just put in a value for this one here, residual volume. We're just saying 0.1 meters. Initial state is closed. Okay, so let's see what happens if it runs all right now when we've done those changes. Yes. Okay, so we've now got the thing. So if I now look at the case there now, pressure at that point. You'll see now that the pressure doesn't go negative. Okay, it comes down to 0. When it gets down to 0, it's letting air into the pipe. Okay, but unfortunately what this has done is also when the pressure then goes positive, it's pushing the air out, and actually as all the air comes out, it's then inducing a surge, which is now getting a 15 bar, which is significantly higher than we had previously. So actually, okay, it's letting the air out and in, but it's causing other problems. And what we can do is you can actually look of I think we can actually look at the air. Also, this component here. So we look at this component. We can actually look at the airflow, or actually the air volume. In other words, how much air has gone in. So basically, when the pump trips, it lets all the air in, 1.2 cubic meters, 1.2 cubic meters, and then it comes down. And actually, if I hold that graph and we actually look at the pressures at the same time on the same graph, you can see how they interact. What we can do is hold that and pull it onto that one there, and you'll see that so initially the pump pressure drops, the air volume goes up and then down, and then all of a sudden you get there's no air left, and you get this slam, you get this water hammer effect. So that's a surge that you want to try and avoid. Let's just have a look at the whole pipeline now. What's happening? We can see the pressure. Let's have a look at the pressure along the whole pipeline. Okay, so the blue line is the steady state initial conditions, okay, and the red lines are the maximum and minimum that you get in the transient. Now what we can do here, so this is just showing you over the whole period that I run the model, which was 200 seconds. Okay, there is this, we can get a bit more information out of this. Time navigator is what I'm looking for. I'll just put it up to the maximum speed. And what this is going to do, if you look up here, it's saying 0 on 200. So in other words, that's time 0 out of 200 seconds. And that's what the blue line is showing you at time 0. And if I press the start, the clock is going to start winding forward. And as it starts to wind forward, you can actually see what's happening to the pressure in the pipeline. So I'll just go back to the start again. And stop 1 minute. So that's the steady state. Okay, and when we start this up, I'll just start it initially a bit slower. So when we first start it, the pressure at 1 second, right, the pressure drops off, and you can see the pressure wave dropping, going all the way along the pipeline. Okay, until it gets to the end, and then it'll be reflected and it'll come back. And if you look at the blue line, the red line at the bottom there, that's the minimum pressure it gets to along the bottom, and that's where that's captured. And clearly the pressure is going to start rising and going up to the top. So I'll just speed this up a little bit. And the pressure should start to rise. Yeah, okay, there you are. So now it's starting to rise all the way up to the top. And that's, so from a design point of view, you're going to have to design for the maximum and minimum pressures. Okay. And at the end, it will sort of come to some sort of steady state condition. So if we look again at the pressure here, what I'm going to try and do now is do something to try and get these pressure spikes down. Clearly, if you have to design for these high pressures, it means you need to have a stronger pipeline, and this is not good for the pipeline. Really, what we want to try and do is limit these surge of pressures that are occurring. What I can do here is I can I'll freeze this series, and we'll come back and have a look at it in a few minutes once I made the changes. Just check to make sure there's nowhere else. Let's just have a quick look at that point there. We can have a look at that as well. So I'll freeze that one as well. And that's just freeze all series. Okay. I'll come back to them in a minute when we've made the changes. So what I'm going to do is look at putting a surge tank here at this high point. Now, what I'm planning to use is one of these. Now, this is not the one I'm going to use for this. We're going to optimize it for the actual case. But this is a sort of typical arrangement, and just to show you what's going to happen. What we're going to have is we're going to have a tank, so that when the pressure goes down, the fluid, we're going to have fluid in this tank, and it's going to let the fluid out. There's a check valve there which will allow the fluid to come out without any with minimal resistance. Okay, and then what will happen is the flow will come back in the other direction, but instead of coming through this check valve will close, and there's an orifice, and that will effectively apply a resistance. It will take the energy out of the system, and it will slow the flow down coming back into the system. And using this system, we can damp out the surge. Now, as I say, these are just some numbers for a different project I was running, but we will use the same sort of basic effect. Just as a matter of interest, this air vessel here has an air vent on the top, so it does actually have an air vent, the same as what we had before. It's got what they call a dipping tube coming down, so actually the air level, the effective where the air comes in is at this level. So as the flow comes into the tank and fills it up, it comes up as high as this dipping tube, and then the air vent is closed, and then effectively the air that's in this area here, if you can see that, is compressed, and that takes the final bit of the system. It effectively pressurizes the system. Okay, so that's what I intend to do. So let's look at an air vessel to do that, and we'll just use a simple air vessel, surge tank, non-vented. We need a vented air. Right, so that's the one we're going to use, a vented tank. What I can do on this is you don't actually have to disconnect it. We can just say disuse. So in other words, it's going to be not used anymore. It's grayed out. So that's now defunct. Just move that over a bit. Okay, so we have this air vessel. What we also need is, for that system to work, is a check valve. Okay, and we need that orifice plate. And there is an orifice plate, if I can find the right component, there. This valve here is 250. We can have that the same size as 250. Okay. Initial state. It's going to be closed actually to start with. I think we need to put that to closed, because when we start off with steady state conditions, this is already going to be closed. I'm not quite sure what's happened here. That's better. This one here, the orifice plate. So what we'll do is we'll start off with an orifice plate quite large. So we'll say the pipe diameter is 250 and the throat we'll say is 100 millimeters. Okay. Now, the surge vessel. What size should the surge vessel be? Well, actually, if we go back to this component, and we've still probably got the results from that, air volume, I think the clue is that we were sucking in 1.2 cubic meters of air. So if we make this air tank larger than that, or the working volume larger than that, then we should have sufficient air volume in here. So what we need to do is set up this tank correctly. If the level there is 15 meters, I think the bottom of the tank should be 15.5 meters. Okay, we set the area to 1 meter, a sort of a minimum of 1.2 or 1.5 meters working volume of gas or water in there. So if we go back from there, so if we have 15 there, we want the air valve to be 1.5 meters higher, because the air is 1 meter, so that's 16. So we say that's 17 meters, and then we probably want the top of the tank to be another meter above that, so that's 18 meters. Now what I'll do is we'll run the model, and later on we'll come back and reduce this. Clearly, when you're doing vessels like this, size is money. The bigger it is, the more it's going to cost. So you want to minimize it. But what we'll do is we'll just set it up initially like this, and then we're going to come back and tweak it and get its size as small as we can. So we'll run the model. Okay, so you need to set up this thing, which is basically the coefficient of heat capacities. Forgot to set that up, 1.4 for air. All right, so I forgot to put that in as well, which is the loss coefficient, and I'll just put a value of 1 in for that. Probably forgot something else. Let's see what happens. Oh, that's okay now, run. Okay. If we go there, we get the pressure. Right, so we've got a pressure case there. If I go back to the one I saved earlier on, so this is the one I saved previously. And what we can do is we can show that onto there. So it's started to help. So it's actually reduced the maximum pressure that we've got. But I think we can do a lot better than that. Let's just look at the level in there. Third volume. So that's going up and down like that. So what we want to try and do is get it down a bit. And I think the best way to do that is actually probably tweak this this thing here. So if we come down to say maybe, let's say 20 millimeters, what happens then? Let's run the model again. We're just going to fiddle around with that until we get it a bit better. I don't need to do anything. Well, that's pretty good, doesn't it? It's yeah. So the pressure's dropped, flows come out. Actually, what we need to check though is what's happening down here. So we're getting quite a lot of fluctuation. Yeah, that's not too bad. But let's just see then. If I reduce that to 10 millimeters, I think that's probably going to go over the top, but we'll just see what happens. So it's starting to get worse in terms of pressure fluctuation. So about 30 millimeters. That's very good, isn't it? So we can leave it. We'll leave it like that for the time being. That's pretty good down there as well. So everything that looks pretty good. Okay. So if we look at the fluid level in that tank, which is this one here, you can see that it's dropping from 17.8 down to 16.2, which is about 1.6 meters. And actually, if you look at how we've designed the tank from the bottom to the top, you know, we've got, well, we could probably take half a meter off there without any problems at all. 17.5, and the top level air inlet 16 meters. So let's see what happens now. Rerun the model. That's probably a bit. It's just 15.5. Okay, let's try that then. So we're coming down, the bottom layer of that tank is 15.5, and we're coming down to 15.9, and the top is so we're using most of it there. That seems to be sort of reasonable, and looking at the pressure that we're getting from there, that's pretty good. So I think that's the solution effectively for that particular model, and we can now sort of just have an overview of the whole thing. So if we look at the pipeline, that'll help with the whole pipeline. We can look at the pressure. And well, as you see there, the blue line is the steady state condition. And after we've done those changes, the maximum pressure doesn't increase. There's a little bit up here where it gets a bit bigger than the steady state. So actually that looks pretty good to me. Obviously the minimum pressure does drop down when you start, but it looks like that would be a good solution for the system, and it won't be too costly because we haven't got too high pressures to design for. And we can just briefly run the time navigator, and let's see what happens. This is showing you what happens, as the pressure goes up and down in the pipeline. Okay, in my opinion, Wanda is a very flexible tool for modelling hydraulic systems and conducting surge analysis. The results you get are very accurate and model the real world very well. For this demonstration purposes, the model I made was actually fairly simple. Okay, I didn't put in all the detail that you would get in a real system, but the tool is very adaptable and you can make the system significantly more complex than what I've shown you in this brief demonstration. If you have any general questions on this, then please leave a comment on my website blog and I will endeavour to answer any questions there. I can't answer any general questions via email, but if you need some assistance from me on a sort of consultancy type basis to do surge analysis, then please contact me. My details are again on my website. Please subscribe to my YouTube channel. I think the link is over there somewhere. If you found this video useful, then please give me a like. That's it today from Fluid Mechanics. Thank you for listening.